All right, here is the constant velocity particle model review sheet, and you'll notice I've marked a few things up. Just kind of a basic mathematical description of our model so far. So if you were to say, what is our model in a nutshell, it would be right here. That would be the mathematical model that we developed from our initial lab, where the position at any time here is equal to the velocity multiplied by how much time went by. You'll notice that sometimes we say delta t, sometimes we say just t. So this would be how much time has gone by plus where it started, or it would be the y-intercept. Quite often we end up writing it that same thing like this, and you'll see the steps to get to this initial version here down to this version over here. This is what I wrote. I said, since the change in position or displacement is equal to where you ended minus where you started, then if I subtract the initial position from each side, that's where this comes from that delta x is equal to the velocity times how long it's traveling. Or if you solve for velocity, you look like that. A couple types of velocity that we talked about during the class, the constant or average. If we're doing average velocity, make sure you use the total displacement divided by how much time went by. Speed is the scalar way of thinking about a motion. Speed isn't displacement, it's distance. So distance is more like the path traveled, and we're going to see that in a sec. The other things that we're going to encounter in this review sheet is PT graphs and VT graphs, so we're going to review those things. Okay, well, let's start with number one. It says determine the average velocity of the object. So if I look at this, how do I figure out average velocity? Well, I kind of got that right now. Average velocity is going to be equal to the change in position, which is known as the displacement, divided by how much time that went by. So in this case, well, it started at 10 and it ended at 60, so it went 50 in the positive direction. It increased by 50. How much time went by? Well, from 0 to 6 seconds, 6 seconds went by. I can even put units in there. 50 meters divided by 6 seconds. 50 divided by 6, if you plug it into your calculator, it's going to be 8.3 repeating, or 8 1/3. And the units you can see are meters per second. So there's our first answer. Write a mathematical expression to describe the motion of the object. Well, when you've got a graph and you're going to make a mathematical expression of it, if it's already a straight line, it's pretty easy to do. In this case, our y is not y, it is actually x for position. So when we talk about what does the y-axis represent, it represents position, it's measured in meters, is equal to the slope. Now the slope in this particular one is 8.3 repeating. I'm going to keep all the decimals here, and I'm going to include the units, and I'll put parentheses around there just so I notice I'm keeping that separate. The x in this case is equal to time, so I'm going to put time. I could put t. I kind of like putting delta t because it shows how much time goes by, so you don't confuse that. Plus b is the y-intercept. So where is the y-intercept in this question? It's right here. It's at 10 meters, so I'm going to say plus 10 meters. There is our answer. I'm going to just put a box around it. There we go. There's our nice answer. Shown below is a velocity versus time graph for an object. Describe the motion of the object. Okay, I'm just going to hit pause and write my answer out. Alright, here you go. I wrote a bunch of stuff down, so I kind of divided this up into 3 different obvious intervals. So in interval number 1, I wrote the object moves in a positive direction at 4 meters per second for 2 seconds. Then the object reverses direction and moves in a negative direction at 3 meters per second for 1 second, and then the object stops and stays motionless for 2 seconds. Now it says draw a corresponding position versus time graph, number the axes. You may assume the object starts at a 0 position, so we're for sure going to start at a 0. Now before I number things, I just have to think about like what's the maximum we're going to get. Well, first of all, the time's kind of an easy one. The time goes up to 5 seconds. Well, maybe I'll go 1, 2, 3, 4, 5. So we won't use all our space, but if I doubled it, I'd run out. So I'll go like that. So each tick means 5 seconds. Now for position, I'm not sure how to go here. Should I label by 1 or something else? So I guess my first question is, what's the farthest it gets? Okay. here in the first segment, so during this segment over here, it's moving in a positive direction. So here's a big piece on your review. On a VT graph, this area here, this area is going to tell you your displacement. Because think about what's going on here. This is kind of neat. We're going to be multiplying the velocity, that's this section of 4, multiplied by how much time goes by. Right? So looking up over here, that's this, isn't it? If we multiply velocity by how much time goes by, you get displacement. So we're going to get our displacement. So what is, well, this is 4 by 2, so this is going to be 8 meters, and it's going to be plus 8 meters. This section here, when it's moving in a negative direction, this is a block, so if I turn this rectangle here, it's kind of strange to think of it, but the velocity, the side of this side of the triangle is actually negative. So this one will be negative 3. This is here negative 3, and this is 1 second. So when I'm multiplying negative 3 times 1, I'm going to get minus 3 meters. How can I have an answer that's negative? How can that make sense? Well, I'm moving in the negative direction, so my displacement or my change in position will be 3 in the negative direction. And this part here, it's not moving at all, so it's not changing. So what's going to happen is that they told us we can assume we start at 0, and then at 2 seconds, we will be 8 meters away. So if I go up by ones, 1, 2, 3, 4, 5, 6, 7, 8 is at the very top. Then after 2 seconds, I'm at the very top at 8 seconds right there. I'm going at a constant velocity of 4 the whole time. In other words, between this dot and that dot is a straight line because a constant velocity is a straight line. So let's see if I can just kind of help my hand-eye coordination here a little bit. I'm not so good at this. That was supposed to be a straight line. I'm sure you can do better with a ruler. And then between 2 and 3, I go back 3 meters. So by the time I get to 3, I'm going to go back 3 meters. 1, 2, 3. So I go to here. And now I'll be down there. I'll try it again. Now I'll be down there. A little bit better. And now for the next 3 seconds, or sorry, the next 2 seconds, 2 seconds, up until time equals 5, I don't move. Now that doesn't mean I go back to the origin. Be careful. That means I just don't move, so I stay the same. So this is what my graph looks like. Maybe I'll make the line a little bit thicker so I can just see it a little bit better. So it goes like that, there, and comes back. And you'll notice now that we can also say, hey, this slope here, well, it rose 8, it ran 2, equals 4 meters per second. So it's a good kind of a check. Here, that's 4 meters per second. This slope was 4. This slope here will be, you guessed it, minus 3 meters per second. This value of the velocity will be the same as the slope here, and that is 0 meters per second because it is a horizontal line. Okay, so to answer the question, it says, oh, draw. Okay, we did that. How far did the object travel in the interval from 1 second to 2 seconds? Well, from 1 second to 2 seconds, well, I guessed how far did it travel? So in a way they're asking what was the change in position from 1 second to 2 seconds. Well, it ended up at 8 and it started at 4, so it traveled 4 meters. Hey, it kind of makes sense because this is a jump of 1 second and it's traveling at 4 meters per second. So in 1 second it travels 4 meters. Okay. Find the displacement from 0 to 5 seconds. Explain how you got your answer. Okay, so the displacement is the change in position. In other words, where it ended minus where it started. Where did it end up? It ended up at, here it is over here, at 5, right? 5 meters, minus, where did it start? At 0. So the answer would be 5 meters. Explain how you got your answer. Well, I kind of showed my work here. I looked at the end of the graph, 5 meters, and I looked at the beginning of the graph. Find the average velocity from 0 to 5 seconds. Okay, so I talked about velocity, whether it's average or constant or something like that, is essentially the same mathematical model. But when we're talking about average, we need to consider the entire period of time here. So this is the displacement, how it changed its position. It's changed its position right over there, that's my delta x part. That's going to be our 5 meters. It moved 5 meters. In how long? It took 5 seconds to go by. So the answer would be 1 meter per second. Notice you could also say, hey, if I started, here I'll use a different color, if I started here and ended there, those are the only 2 points I'm interested. Between here and here, I could connect those 2 points and say, oh, what's the slope? Well, it rose 5, rise of 5, run of 5, 5 divided by 5, that's exactly this here, is equal to 1 meter per second. So another way to think about average velocities, you could say, connect first dot at t equals 1, or t equals 0 seconds, and last dot at t equals 5, and then find slope. That's one way to explain it. Many different ways to think of this. Find the average speed. Okay, so now we've changed from velocity to speed. So if we're thinking about speed, well, what's the difference between velocity and speed? Velocity is all about vectors and displacement. Delta x is displacement, while speed uses distance. The difference between displacement and distance, we've taken this a few times. We'll say, well, displacement is the difference between where you started and where you ended. Distance is more like the entire path. How long was the entire path? So here the person walked 8. And here, even though they went 3 in the negative direction, you just say, oh, they went 3. How far? First I walked 8, then I walked 3. So for distance, it's going to be, the distance will be 11. So here I'm going to write speed is equal to the distance over the time that goes by. So that's going to be 11 meters divided by 5 seconds. 11 divided by 5, what? 2.2 meters per second. Explain how you got your answer. I guess use distance, not displacement, exclamation mark. Number 3, a bird travels toward 0 position, then suddenly reverses direction. Isn't that an interesting way of saying it? Travels towards 0 position. In this case, it happens to be from a positive place towards 0. So it's going in a negative direction. So we see this going downhill. It's in a negative direction. Then suddenly reverses direction. So we see that happening over here. Clean up my mess. First question is, find the average velocity from 0 to 10. So, well, from 0 to 10, time to get to class. Going average velocity from 0 to 10, from 0 to 10 is actually a straight line. So it's interesting, in this case, average velocity, it's the same thing as the constant velocity because they're going the same the entire period of time. So like we're over here, I said, hey, we could connect the first dot and the last dot and then find the slope. Well, that's, if I connect the first dot with the last dot, time t equals 0 and t equals 10, I just get the regular straight line here. So in this case, it's going to be the change in position, which is, well, if it starts at 30 and ends at 10, it went down 20, divided by the change in time. And how much time went by? 10 seconds. So this is meters per second divided by seconds. So that's going to turn into, oh, sorry, that was meters divided by seconds. So I'm going to get minus 2 meters per second. Find the average velocity from 10 to 20. So again, I'm going to be finding from here to here the displacement divided by the time. So the displacement is plus 10. The time that went by was 10 seconds, so I'm going to get 1 meter per second in the positive direction. Determine the average speed from 0 to 20. So again, speed is going to be equal to the distance over time. Be careful, the distance, okay, so here they travel 20. Who cares if it's positive or negative? They travel 20 meters. Here they travel 10 more, so they traveled 30 meters. Divided by how much time went by? 20 seconds. So that would be 1.5 meters per second. Now determine the average velocity from 0 to 20. So let's use the connect the dot idea. This is turning into a very useful idea. So if I connect these two and just find that slope, the slope between those two, while it would have a rise of -10, it would have a delta x of -10, and it would have a delta t, a run of 20. So it would be -10 over 20, so that would be negative 0.5 meters per second. Boy, a big difference between the average speed and the average velocity. Find the velocity at t equals 5 seconds. Well, at t equals 5 seconds is smack in the middle of that first segment. And we already even found the average velocity, and I think I had to comment that the average velocity, in this case, it's in the middle of a straight line. So from here to here, it's all constant, right? This is a segment where it's a straight line, so the slope is the same throughout. So throughout that period of time, it's going at a constant velocity of -2 meters per second. How fast is it moving here? -2, -2, -2, -2, -2. Here it suddenly changes, right? But that entire period of time, it's going -2 meters per second. You could pick any 2 points along that line and find the slope, and you get -2. Number 4 says a basketball initially travels at 3 meters per second for 3 seconds. So now we've switched to a velocity time graph. It says describe the motion of the ball after 3 seconds. I'm going to pause and write my answer again. Okay, so again I number my 2 intervals just to keep track of things. So for part 1, I wrote the ball traveled in the positive direction at 3 meters per second for 3 seconds. Alright, I'm back and not sure where I was a second ago, but it says number 1, the ball traveled at a positive direction at 3 meters per second for 3 seconds, and then I wrote here it traveled for some number of meters, and I was hoping that you could figure that out. So if it travels at 3 meters per second for 3 seconds, it is actually this area here. This area inside of there is going to be how far it traveled. So that is going to be 3 times 3. That will end up being plus 9 meters, just like we had before. So I could say it traveled plus 9 meters. And in segment number 2, it reverses direction and moves in the negative direction at 1 meters per second for 4 seconds. So you guessed it, during that period of time it moved -4. Now it says draw a quantitative motion map that represents the motion of the object. Don't get too sloppy. If it says quantitative means we want to see some numbers. So I want this actually to be accurate. So the first thing I'm going to say is, I'm going to say that my dots represent intervals of 1 second that goes by. And I've got 1, 2, 3, 4, 5, 6, 7 seconds altogether. So I'm going to get 8 dots because the first one is at t equals 0. To begin with, I'm going to get up to 9 meters. So let me draw my first dot. Here's my first dot right here. And I'll draw the arrows part later. 1 second later, because it's going 3 meters per second, it will be at 3 meters. So I need to get up to 9 altogether. So let me see. 1, 2, 3, 4, 5. You know what? I think I got to make each of these 2 meters. 4 meters, 6 meters, 8 meters, 10 meters. Because if I made each of those clicks only 1 meter, I wouldn't be able to get far enough. So, okay. So that means 1 second later, I'm going 3 meters per second, so I'm at 3 meters. 1 second later, I'm at 6 meters. 1 second later, am I doing this right? 1 second later, I am at 9 meters. And at 9 meters is when I'm going to be changing direction right away. Okay, so let's think about this. Right now, I'm traveling 3 meters per second, so I need to draw an arrow. I draw it about halfway. And this represents 3 meters per second. Here I'm going to draw this one about halfway, this one about halfway. Now I don't want to draw this to the right anymore because as soon as I hit 3 seconds, so this is t equals 0, this would be t equals 1 second, this would be t equals 2 seconds, and this is t equals 3 seconds. So at this point, I'm actually going to be moving the other direction. So in fact, I could even draw this arrow just dot a little bit lower, just so I don't hit the other ones. Now I'm going to be going the other direction. So I'm going to be going in the negative direction. I'm going in the negative direction at -1 meter per second. So in 1 second later, I'll be here. Another second later, I'll be here, right? How many of these do I have? 1, 2, 3, 4, 5 dots. 1, 2, 3, 4, 5 dots. Or another way to think of it is 1, 2, 3, 4 jumps. 1, 2, 3, 4 jumps. Okay, so now I'm traveling the other way, so I'm going to draw my arrow about half the distance to the next dot. And these are pretty consistent. At the end, I'm still traveling in that direction, so I'm actually going to put my last dot in there. So this is this one's t equals 3, this one's t equals 4, 5, 6, and this last one is at t equals 7. This one lines up with 5 meters. So I start here at 0 meters and I end up at 5 meters. Okay, going forward direction, changing and coming back the other direction. How far did the ball travel from t equals 3 to t equals 7? Well, here is t equals 3, t equals 4, t equals 5, t equals 6, t equals 7. So it traveled from here to here. So how far did it travel? It looks to me like this was at 9, and it went minus 4 meters. Or if I wanted to look at my velocity time graph, from 3 to 7, that would be this area, and that area would be minus 4 meters, just like I said here, minus 4 meters. Number 5, a race car reaches a speed of 95 meters per second after it is 450 meters past the starting line. If it travels at a constant speed for the next 12.5 seconds, how far will it be? Use the appropriate mathematical expression and show how the units cancel. Well, you know, I'm just going to start off by drawing a position time graph, because what we did is first we did a graph in this beginning of this unit, and we took the graph and we turned it into a mathematical expression, right, based on the old y equals mx plus b thing. And I want you to notice that we're not interested in this period of time. This is an interval of time. I'll just give it a, like before I did. And first it speeds up, reaches a 95 meters per second. We don't need that. We want to go, once it's gone there, now it's going at a constant speed of 95 for 12.5 seconds. So I'm going to draw a position time graph. And it says I'm going to start at 450 meters. So I'm starting here at 450 meters. And I'm going to start at time 0, and I'm going to go for 12.5 seconds. And where will I fit this constant speed of 95? Well, I'm going to be moving in the positive direction. So this will have a slope of 95 meters per second. So when I do my mathematical expression for this, hey, this is a straight line, so my y here will actually mean my position. Actually, no, I'm using x here. My y will be position, which is x. My slope is 95 meters per second. My x is how much time has gone by, plus my y-intercept, which is 450 meters. Okay, so there we started with our graph, and now we have a nice mathematical expression. And then it says show how the units cancel. Well, how much time goes by? 12.5 seconds. So I'm going to put 12.5 seconds in here. So this is the best way I can show. When I multiply these two together, meters per second multiplied by seconds, those are going to cancel, because I'm going to have like meters times seconds divided by seconds, so they cancel because they're in the numerator and the denominator. So that part is equal to 1. Okay, so 95 times 12.5. I got to get my calculator out for that. I guess that would be 1187.5, and this is meters. So that's how far it went because of how fast it was going. And because it started at 450, we need to add that part in there. And so we get 1637.5 meters. Okay, I hope this review was, that's it. I hope that review was helpful for you. I'll see you in class.